All right, here we go. So we're gonna do 4-4 today, which is just the counting rule. So we're gonna find the total number of outcomes in a sequence of events using the fundamental counting rule. It's actually pretty simple. Just multiply all your options. So if like you're making a sandwich and you have like, I don't know, 3 pieces of bread, 5 different meats, 4 different cheeses, to figure out all the different combinations, you would just multiply all the numbers together. Yes, sir. Um, I'm gonna go with user error, but I have no idea what's up with your calculator. All calculators should give you the same answer if you're putting it in the same results. If you put what? Oh yeah. So that becomes a user error though. Like for these calculators, if you don't put parentheses around a negative and square it and stuff like that, it doesn't square the negative. Yeah. So I don't know of any calculus that have been wrong on what you've typed. All right, so there we go. So the fundamental counting rule is there's a sequence of n events in which the first one has k1 possibilities, and the second has k2 possibilities, and the third has k3 possibilities, and so forth and so forth. The total number of possibilities in the sequence will be the products of the number of possibilities in each event. So like I said, if you had 4 breads, 5 meats, and 3 cheeses, you would literally just multiply those, and then you would get 60 different combinations. And that's the fundamental counting rule. That just tells you how many options you have. If you're trying to find a probability of getting a turkey sandwich, then you'd have to do a little extra on finding your combinations. Notice the word and though. What does and mean? Multiply. Very good. What's the word or mean? Add. Very good. Remember those things from the previous section. We all good with this? All right, let's get into an example. We just finished up 19, and I think we're on 20-ish. Huh? I did. I saw a lot of you at the fair. Oh yeah. It's weird to be called outside to like this work area and go, hey, Mr. Smith. Mr. Smith. I still got kids that I've taught like 11 years ago that say Mr. Smith. I'm like, at this point, you're like in your late 20s as well. So I'd probably respond faster than I would if you said Mr. Smith. I do respond to emails. Oh. All right, so we're gonna calculate how many different hats. So it says a yarn shop has hat patterns in 4 styles, 5 stitch options, 3 sizes, and 8 yarns that are appropriate for the hat. Go ahead. Maybe. I'm not a hat person, so I don't know. The pattern was what? Oh, good to know. Perfect. All right. So how many different hats can we made? How many hats can be made in size? In size is disregarded. So again, all you're going to do is you take each option. You have 4 styles, 5 stitch options, 3 sizes, and 8 yarns. You take all options and you multiply them together, and you end up getting your total number of options you have. Oh, technically, sorry. Yes, I did make it to the next question. If the size is disregarded, I need to take the sizes out. So you can either re-multiply by 4 times 5 times 8, or you can easily divide this number by 3 to take the 3 out. You are correct. Yes. So what they did is they just re-multiplied it and said 4 times 5 times 8. or divide that by 3 and you still get 160 options. So if sizes don't matter, you have 160 different options. If size does matter, you have 480 options. Good. And let's see, do we have a word and? Oh, yeah, no, that's a listing of all your different options. The word or would be like if you had this, or this, then you would add them. Yeah, go. I'm okay, thank you. All right, so in the next example, the sample space for each event will be the same. However, in one case, repetition is allowed, while in the other case, repetition is not allowed. All right, and we kind of saw this with things being put back in or kept out. We all good with these? So basically, repetition, like on this one, if I'm looking for all the possibilities, repetition can't happen. Well, it can't be like I can't do like the same style, the same stitch, the same size, and the same yarn twice. It'd just be like as long as it's one of those four things. There are some things that can repeat in a sense that if order matters or if order doesn't matter. If order doesn't matter, then we can have a lot of repeating things. If order does matter, it actually shrinks our stuff down because if something happens, then it can't happen again. If order doesn't matter, if something happens, it can happen again way over here as well. And we'll look at some of those cases today, talking about combinations and permutations. All right, so example 21 here, it says in the lottery game called Pick 4 is played by picking 4 digits between 0 through 9. How many sets of 4 digits are possible if digits can be repeated? Meaning I can get a 1 on the first draw and a 1 on the last draw or 1 on all the draws. So things aren't basically, I'm not taking anything out and then not putting it back. Everything goes back in the pot. That's exactly what you're doing. Yep. So, okay. So again, can be repeated. So how many sets of 4 digits are possible if digits cannot be, two separate questions. Sorry. So if it can be repeated, how many numbers are there? How many numbers are between 0 and 9? 10 numbers. 0 is a number 2, right? So there are 10 different numbers they can choose from. And then you're going to pick 4. It can be repeated. So that means how many options are on the second number? Still the same because I can get the same number. So you'll see if I can repeat, then I can have 10 options the first time, 10 options the second time, 10 options the third time, and then 10 options the fourth time. So if it can be repeated, the number of options don't change. So therefore, I would just multiply that by however many picks I'm doing, and I'm picking it 4 times. So what is 10 times 10 times 10 times 10? Yep, just add all the zeros. So there's 10,000 options you could choose for to win the lottery for pick 4, right? So you have a 1 out of 10,000 chance. Now, the odds go less if it can't be repeated. So if I get a 1 the first time, I cannot get a 1 the next time. So meaning, how many options do I have the first time? I have 10. But then the second time, if I can't repeat that number, how many options do I have now? 9 and then 7. So if there's only a 4 pick lottery ticket here. So then I would multiply all these, and 10 times 9 is 8 times 7 is, oh, I thought you said 56. Sorry. Good. And then just multiply those two. It's probably easier to put it like this. 6 times 9 is 54, 45, 49. Is that what y'all got? Because 9 times 5 is 45, is it not? I know. 45 plus 5. You're right. I don't know. For instance, my head just turned it over to a 45. All right. Thank you, Ezekiel. Keep me on my toes. So 54.40. All right. So then you can see 50. What? 9 times 5 is 45. It's 50, not 49. It's not a good day, guys. All right. 5-0. It's always a good day. All right, so you can see basically if my numbers don't repeat, I basically have my odds cut in half. I have a better shot of guessing the numbers in the correct order. Any questions on lottery tickets if things can be repeated or not repeated? All right. Yes. I think. Actually, I don't know. It depends, but I don't think it's out of 10 numbers. I think it's like out of 50. I think it's like 0 to 50 or something like that. Yeah. They do too. They get a lot of money. All right, so let's talk about factorial formulas. We talked about this a little bit last week, but factorial is basically that number times itself in decreasing order. So a 5 factorial would be 5 and then times 4 and then times 3 and then times 2 and then times 1. And that would be what that is. Oh, there's a theorem out there on why 0 factorial, because 1 factorial is 1, 0 factorial is 1. What is the that could be a good one. No, it won't be. It'll be 1. You can't have negatives. What is the theorem? It's been a long time since I've seen it. No, they're right. Let me look it up and I'll come up with something tomorrow. I got to remember it. I haven't seen it in a long time. I'm not going to ask you for the proof. I just might ask what's 0 factorial and have options, and you guys have to know it's 1 or something. Yeah. Yeah. I'll have to think about it first before I can just go find it. All right. Any questions on factorial? Okay. We're probably going to get into this here in a second, but I want to show you this anyways. If I have like 10 factorial over 5 factorial, okay, this is about to come up, I'm sure. This ends up actually just being 10 times 9 times 8 times 7 times 6. Because 5, 4, 3, 2, 1 on the bottom will cancel out the 5, 4, 3, 2, 1 on the top. Then you do it because there's some like this. You'll have 5 factorial times 3 factorial or something like that. So you'll still have 3 times 2 times 1. That's 3 times 2, which is 6. So cancel out that 6. Yeah, you can do that kind of math, yeah, but not squared, no. Yeah. It depends on how many. It could be something like they might have 3 times like 3 factorial something. So they had 3 squared, then times 2 times 1. And at that point, it was able to cancel out a 9, 2, and a 1. That's also something they could do. You That's fine too. You can do it that way. It's the same thing as multiplying a whole bunch of fractions. Yeah, both of those work. Yeah. Any other good questions like that? We're probably going to see a whole bunch of these here in a second, but I just want y'all to know that. All right. Objective 6 is finding the number of ways the R object can be selected from N objects using the permutation rules. Permutation. So a permutation is an arrangement of N objects in a specific order, and that means that order matters. Meaning if I put Ezekiel here in first place, Ezekiel cannot be second or on. So order matters. When we get into combinations, And I'll put this in order. You're all about to run cross country, right? If Ezekiel gets first, that means Rivers and Ella, you cannot. Oh, it's not all together? I just assumed y'all ran together. Okay, whatever. Okay. Ezekiel, you're out. Ella and Rivers, y'all are running. Rivers gets first. Ella cannot. That's permutation. Order matters. But if I'm just taking two of y'all to the cross country meet into the vehicle, then it doesn't matter who went into the car first because you're both in the car. So that's combination. So order doesn't matter. If Rivers gets in, then Ella, or Ella, then Rivers, you are both in the car. I didn't hear anything you just said. Well, then it gets more specific. If we're talking about who gets to sit specifically in the car, like shotgun or back seat or something, then order is going to matter. But if I'm just asking people to get in a car or in a bus or something like that, order is not going to matter because they're on the bus or on the car. Right? So that's a big the difference between permutation and combination is permutation order matters. So first consider the instance where all n objects are different. When all objects are used, then the permutation of n objects in at a time is written by npn and calculated using the formula npn n factorial or n factorials. All right. So there you go. Hopefully they give you the equation, because if not, I got to teach you how to do this in the. Oh, good. They give you the equation. All right. So here we go. So permutation number one. When R of the n objects are used in a specific order, I was going to go with same order. Specific order, the permutation of n objects are at a time is P or NPR, which is going to be this. This is what you need to memorize. For combination, that's going to be just about the same, but I think it's n factorial over n times n minus r factorial, something like that. It has like another r, that's it. Yes, so if it's a specific order, it's permutation and it's going to be this one. If order doesn't matter, then it's combination and it's going to be the other one. Go ahead. Oh, will the R ever be bigger? No, but it can be the same. Say one more time. Uh-huh. Oh, yes, true. Yes, I got you. On the formula. Yes, sir. Go ahead. No. It's still going to be, yeah, it's still going to be 0 factorial. So if R is the same thing, let's say R is, let's say I want to know the 32 different combinations out of 32 combinations or something like that, then n and r will be the same situation. So you read it as 32 minus 32 factorial, but 32 minus 32 is what? So you're thinking that 0 on the bottom of a fraction can't happen, but it's 0 factorial, which we now know is 1. So you really just have 32 factorial on the top, which is what it was saying earlier. If r equals n, then it's just going to be npn rather than npr. Do I need to turn off the lights? Because the sun seems to be glaring. Better, worse? I don't know. Maybe some sunglasses. All right. Any questions on that rule? Yes, go ahead. Huh? Can the rule? Are you asking me to turn off the lights? It doesn't have to be a rule, but I can turn off the lights if it makes it easier for you. All right. Let's do a problem with permutation. All right, so in example 22, it says ways to visit patients. So suppose a home nurse has 6 patients that must be visited in one day. How many different ways can the nurse visit them? And then B, if the nurse must choose 4 to visit in one day, how many ways can that be chosen? So if all 6 patients must be visited, then there are 6 patients that can be visited first. So then 5 then can be visited second, then 4, then visit third, and so forth and so forth. So what this is basically stating is order matters. So if I see one patient, I can't go see that patient again, but I have to go see all the patients. So in this option A here, I have 6 patients I have to go see, but I have to go see all of them. So therefore my P or my N equals my R. So I can plug it into this formula of N factorial over N minus R factorial. And I would get 0 factorial, which is 1, and then just back to N factorial. That's what that first statement said earlier. So in this case, to figure out how many ways, I just need to do 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. Right? I guess I have no 6 times 3 is maybe if I can do this right, 30, 60, 180, 260. 6 times 5 is 30, right? Oh, that's right, because 30 times 4 is 120. Yeah, 120 times 3 is 360. Then double that, 720. Yes. All right, note the formula works here because 0 factorial is defined to be equal to 1. So therefore, this is what it gives you if you use the formula as well. Any questions? 720. All right. Now let's go back and answer that second question, which is she can only visit 4 patients. That changes the formula. That makes it where N is still 6 because there's 6 options, but now R is going to equal 4 because she's only going to go visit 4 patients, right? But the concept is still there. It's still going to be 6 times 5 times 4 times 3, but then we would stop there. So to use the formula, that's it right there, 6 times 5 times 4 times 3. But in the formula here, it's just 6 factorial on top, then 6 minus 4, which leaves you with 2. 2 factorial is 2 times 1, and I can cancel out the 2 times 1, and I still get this 6 times 5 times 4 times 3. So at permutation, sometimes it's still quick just to do the simple fundamental counting theorem by just multiplying however many options you have for each situation, or you can use the formula. Both of them work. Does that make sense? It's just part of the factorial. You don't have to write it because it doesn't do anything. All right, 6 times 5 is 30. 30 times 4 is 120, not 60. And then 120 times 3 is 360, not whatever I was saying earlier. Right? So if I can only go see 4 patients, then I have 360 options versus the 720 if I went to go see all of them. All right, let's look at another permutation question. So now consider that some of the objects are identical. So permutation number 2, the arrangement of N objects in a specific order using R1 objects are identical, R2 objects are identical, all the way up to RP objects that are identical. Then you would get something like this, where it's N factorial divided by however many identical ones factorial, how many of the second one factorial times however many of the third factorial, where in fact, all of these repetitive things will still represent how many objects I had to begin with. So to put numbers to that, so arrangements when some objects are identical, how many permutations of the letters can be made from Mississippi? Best thing to do is write all your options. How many M's do I have? How many I's do I have? How many S's? How many P's? 2. All right. So therefore, those are all your R values. Oh, it looks like it's already written here. So there are 11 letters. That's how many options you can choose from, but I have only 1 M, 4 I's, 4 S's, and 2 P's. All right. So therefore, my N factorial over R factorial, R1, sorry, times R2 factorial times R3 factorial times R4 factorial. And those are all the different options I have for each letter. So that's how they get from 11 factorial on top. My M only had 1 option, so that's 1 factorial. My I's, I had 4 options, so that's 4 factorials. My S would be 4 factorial because I had 4 options. And then my P would be 2 factorial because I only had 2 of those options. And now I can calculate how many options I can get, because the issue is when you draw an S, you don't know which S it is. It's just an S. So those combinations kind of combine, right? So we don't have as many as if it was just 11 completely different letters. If it's 11 completely different letters, we can simply just say 11 factorial and then just figure that out. All right, so now when this happens, to kind of show you the math here, this is going to be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, I don't even going to use that 1 factorial. I have 4 times 3 times 2 times 4 times 3 times 2 times 2. All right. And then what they did is they're going to simplify this. So I don't need that 1. I can eliminate one set of 4 3 2s. Because I have 2 sets of 4 factorials. So I have 4 3 2 1, 4 3 2 1, and then 2 1. I just didn't write the ones because they're not necessary. So now I see that I got I got 2 times 4. Okay, that would make 8. I got 3 times 2, so that'd give me 6. So it looks like this ultimately is just 11 times 10 times 9 times 7 times 5. And then we can kind of make that a little bit cleaner. If you didn't see that, you could just multiply all the numbers on top, all the numbers on bottom, and then simplify that fraction as well. You'll get to the same conclusion. I don't feel like doing this one, so I'm going to do 11 times 10 times 9 times 7 times 5. And so you have 34,650 options when you have repetitive letters. But notice, had none of those letters repeated, I would have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And I would have 39,916,800 options had all those letters been different. So the fact is that because we don't know which I we're picking, which S we're picking, which P we're getting, we're going to just grab it. We don't know which one it falls into. It drastically reduces how many combinations you can have. Go ahead. Then you have to take that result and divide by 6. Okay. Yeah, like if I couldn't, like if I had 3 and 2 left over here, let's say I had already got rid of the 6 some other way, then that 3 and 2 would become 6 on the bottom. So after I got this top number, I would then have to divide that number by 6 to figure out the actual combinations. That's a good question. Ezekiel, I'll turn those lights back on. Any other questions there on that type? So that's what you do when order matters and you have repetitive options that all kind of look the same. That would not have been in 4.3. That would have been on 4.4. 4.4 was open. 4.4 was open. And a lot of y'all had attempted 4.4. Actually, I think all of y'all attempted 4.4. Yeah, technically, but I just changed it to this Sunday. I thought I already changed it Thursday. Yeah, and then I don't know if your answers got answered because by the time I got to my phone, I was already out in the field, so I didn't. Yeah. Okay, because I was like, I just need the mean, and that could answer the question. Yeah. All right. So I like to say I'm always on my phone, but there's sometimes I'm just not on my phone. All right. So the next thing we're going to talk about is combination. So when the number of objects can be selected from n objects without regard of order using this combination rule, you'll find out that you have like less options if order doesn't really matter. Or maybe I guess order doesn't matter. You probably have more options. Yeah, I don't know. We'll look at it. We'll investigate. I think it's going to be less. I think it's less options. All right, so a combination is a selection of distinct options without regard to order. So combinations are used when the order or arrangement is not important, as in selecting process. Suppose a committee of 5 members can be selected from this organization membership of 45. This 5 selected members represent what we like to call a combination. So again, notice here, I have basically think of student council. There's 45 of y'all. I just want 5 people to be in charge of homecoming. All right, cool. Those 5 are all going to be in charge of homecoming, but it doesn't matter how I selected those 5. They're all still being part of homecoming. It gets different when you think of the same situation as student council. 5 people are going to be an officer, president, vice president, secretary, recorder, whatever another one is. So if so-and-so gets president, they can't be any of the other options. So now this is a permutation where order does matter. If I'm just selecting 5 people to be in charge of something and there's no title to it, they're just in charge of it, that's combination. It doesn't matter which 5 I select. If Ezekiel's the first pick or the 5th pick, he's still in charge of homecoming. Right? Does that make sense? Yeah. So the combination rule then is this guy, and you need to specifically know this one. Right? Those 2 are going to be big on your test. And again, remember, this is a no notes test, so you need to know your equations. But the only difference here is they add in an r factorial on the bottom. We all good with this? That's a period to end the sentence. Right? There is ways to type it in a calculator with these n's and p's, and I don't remember those. No, I just go with the formula. Yeah. Yeah. For this one, because there's a lot of mean, median, mode you might have to calculate. So y'all can use that to help you out. I'll try to keep the numbers pretty small though for you. Huh? How tall? 12 and 11 3/4 or something like that. The same length and width of regular paper. Oh, I don't know. However many it takes to put 25 questions on it. Oh, okay. All right, so here we go. So playing bridge. So it says how many different tables of 4 can you make from 12 potential bridge players? So again, order is not going to matter. You're all playing at the same table as long as those 4 are there. Doesn't matter where they're sitting, they're still at that table. All right. So this is now a combination. And it says the question is how many different groups of 4 players can be selected from a potential of 12. So 12 would be your N. And then your R is equal to 4 because that's how many you are selecting, which it already wrote it down here for you. So again, this is a combination because order is not going to matter. They're all sitting at the same table. So there's your NR. So there is how you can technically write it. So if we're doing the math behind it, remember it's N factorial on top. So it's going to be 12 factorial. And then on the bottom is going to be N minus R factorial. So that's going to be 12 minus 4 factorial times the R factorial, which is going to be times 4 factorial. So when we work this out, I get 12 factorial over 6 Nope, that's not how you do math. 8 factorial times 4 factorial. Also, one thing to note, what are these two numbers added up to? 12. That's going to happen every time. Whatever these two numbers are after you do the subtraction need to add up to how many options you have. Exactly. All right, to make our life a little bit easier, we write this out. I'm going to delete 8 factorial from 12 factorial, so I'll be left with 12 times 11 times 10 times 9. And on the bottom, I would still have 4 times 3 times 2 times 1. Does everyone see how I just did that? So I just took the 8 down away, so that basically canceled with those. So now I can simplify more. What else can you see? 4 and 3 make 12. So that 12 now goes away. And then technically you can make this 2, simplify this 10 by 5. And now your real question is, what's 11 times 5 times 9? Times 1, yes. So 4 times 3 was 12, so I was able to delete the 12. And then 2 can go into 10 5 times, so I was able to reduce 10 to 5. If you didn't see that, again, you could do 11 times 10 times 9, take that result, divide it by 2, and you get to the same conclusion. That's fine with me. Whatever you find easier. All right, so there's 495 options of turning 12 people into groups of 4. All right. So I guess that's the same question. It says there are 495 possible different bridge foursomes. Questions on any of this? Making a little bit more sense now that we're seeing it versus what you might have seen if you opened up the homework. I pushed, instead of having 2 days on 4-5, I'm just doing 4-4 today and 4-5 tomorrow. Are we done? Is that what y'all want to do? Then we could do homework questions tomorrow at the conclusion of 4-5. All right. All right, let's do it. I still have an example. Y'all don't have a example 25? Okay, let's finish that example then. All right, I like it when they don't give us the answer because then I feel like we can actually do it. All right, so if a person can pick 3 presents from 12 presents under a Christmas tree, how many different groups of presents can be chosen? So what's my N? Okay. What's my R? 3, good. Does order matter, yes or no? Does it? It just, yeah, you're just picking 3. If I pick the big golden one first or third, it's still going to be one of the 3 I get to pick, right? So the order is not going to matter. Maybe it's a single, it's a one child in the home. Yeah, it's one child in the home, so they already assume it's going to be for the kid. All right, so when we know that order doesn't matter, we know it's going to be a combination equation, which again is n factorial over n minus r factorial times r factorial. Here's the best way to practice memorizing your formulas. Write out the formula before you fill in the numbers every time, so then you can have it memorized pretty good. Do it in your head, that's fine. So this will be 12 factorial. This is 12 minus 3. If y'all skip this step, that's completely fine. I probably would have as well. Times 3 factorial, now looking like a question mark. So this is going to be 12 factorial over 9 factorial times 3 factorial. Again, check to make sure you did your math right. These two numbers need to add up to this. I'm going to delete the 9. So that's going to be 12 times 11 times 10 divided by 3 times 2 times 1. You guys see anything y'all can simplify? Go ahead. Yes, but what am I waiting on? Oh. Say it one more time. Oh, you could do 3 times 2, which is 6, and make 12 become a 2. And then you could have easily done this as 2 times 11 times 10 as well. Because you would still get the same outcome. Just I want to point something out real quick. Olivia had a good point here. If you did 3 times 2 and got 6, you could put 6 into 12 2 times and do 2 times 11 times 10. But notice what's 4 times 5 was 2 times 10. So the outcome is still going to end up being the same, no matter how you reduce it. Right? Any other questions there? So we're good on permutation and combinations. Those are probably the hardest thing in probability. All right, let's look at 4-5, which is probability and counting rules all combined to wrap up this unit. I'll just do a bunch of circling. I like they're just random circly things. Yeah. On yours? Okay. We'll get to it if we need to. All right, so probability and counting rules. So in this objective, we're going to find the probability of an event using the counting rules. This word, the keyword. No, I'm kidding. It's not. It's not a keyword. It's just. All right, now that we have learned the fundamental counting rule, the permutation rule, and the combination rule, it is possible to compute the probability of outcomes of many experiments just using these three rules, depending on what situation you are in. All right, so in example 26, it says scheduling workers. Suppose a manager supervisor has 16 women and 12 men. Each shift needs 8 people. First thing we want to do is find the probability that exactly 3 women are selected to work the shift. Doesn't look like they have, oh, it does. We'll just check our work below it, make sure we do it right. All right, so here we go. So I'm going to put the work here. The answers are obviously at the bottom. But if we're trying to find the probability that exactly 3 women are selected to work the shift, does order matter? No, it doesn't. I'm just trying to get 3 women. All right. So it does. That is a good point. Go ahead. Yes. So it doesn't matter because I just need 3 women and 8 men, or sorry, three women and 5 men. All right. So if I want exactly 3 women, what does my 3 represent? R. And then my N would be what? I think it's going to be 16 instead of 28. Because there's 28 to choose from, but you want the first 3 to be women. So I'm going to go with 16. So I'm going to go with this key word here exactly is a key word. It's not that what's the probability of 3 of them being women. What's the probability of 3 of them exactly being women? So my options are only out of 16. Yeah. Well, okay, but that's the first. So what we're gonna do is to find the first 3 have to be. Let's just say the first 3 are gonna be women. It doesn't have to be, but 3 of them are gonna be women. That's gonna then be 16 on top. And this is order doesn't matter, so that would mean that this is gonna be 16 minus 3 factorial times 3 factorial. That's the first 3 selections. You then need to go find the next 5 selections. Huh? It does. I don't want any more women. I wanted 3 exact women. So the other 5 must be what? So now the other 5 have to be men, but how many men do I have? So now it becomes a 12 factorial over 12 minus 5 because it has to be 5. Because again, I want exactly 3, not at most 3, not at least 3, exactly 3. So that means the other 5 have to be men. So there's my other combination there. All right. So then we can do this work. So after this point, this will be 6, bless you, over 13 factorial times 3 factorial times 12 factorial over 7 factorial times 5 factorial. Bless you. All right, so 16 times 15 times 14 over 3 times 2. So y'all got here? Because this would be 12 times 11 times 10 times 9 times 8 over 5 times 4 times 3 times 2. So what y'all got? That's what a factorial is. Oh, going by the counting rule that we did at the beginning of 4-4, that means you multiply all the options that you have. These are the options I have for each set. I see 14 can turn into a 7, and I see 15 can turn into a 5. Over here, this 2 can make this a 4. This 3 can make this a 3. This 4 would then cancel that 4. And this 5 would make this a 2. So this is what I got. 16 times 5 times 7 times 12 times 11 times 2 times 3. Is that what y'all got? I think that would work as well. Yeah. I just put, well, just do your multiplication. Do your multiplication. Let me do my multiplication and see if we're all right. Yes, we're still multiplying all together. So I'm going to see if we're all right. Don't look. Yeah. Did y'all get the same answer? Oh, okay. Yeah. All right. So it doesn't matter how we reduce as long as we're reducing correctly. All right. Now here's the issue. We're trying to find the probability, not the amount of combinations. So you just found all the different combinations of getting exactly 3 women out of basically 28 people. You would have to divide that by however many combinations there are in total. (28 to the 8th power). Yes. Yeah, so there is 28 total people here, and I'm selecting 8 of them. This is 28 to the 8th power that needs to go on the bottom. I don't know that one, do y'all? Where order doesn't matter, you could, but it would be 28. The N and R would both. Well, no. Okay, I see what you're talking about. Different alternative. I bet this equals the same thing. And I'm curious. If it's an order doesn't matter, N would be 28, but my R would be 8 because I'm selecting them. So that would be 28 factorial over 28 minus 8 factorial times 8 factorial. Yep. So that would then be 28 times 27 times 26 times 25 times 24 times 23 times 22 times 21 times 8 times 7 times 6 times 5 times 4 times 3 times 2. I bet it's the same thing. I'm curious. All right, then I'm going to just multiply it out. So 28 times 27 times 26 times 25 times 24 times 23 times 22 times 21. Divide that by parentheses 8 times 7 times 6 times 5 times 4 times 3 times 2. Is that what you got? 28 to the 8th power? Oh, it gave you an E. I don't think it's going to be 28 to the 8th power. It can't be 28 because if I select one of those people, it's going to be 28 to the factorial 8 times. Because I have, yeah, it's going to be 28 times 27 times 26 times 25, 20, blah, 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 all the way down. Yeah. So that would be the total options then. And so your probability is 443,520 out of 3,108,105 combinations. And when you do this decimal wise, 0.1427. So you have a 14% chance of getting 3 women, exactly 3 women, in your 8 shift manager position or whatever. Yeah, I think so. So it's technically, it should be 28 times 27 times 26 times 25 times 24 times 23 times 22 times 21. Yeah, that still would be wrong. Yeah, it has to be the combination one. What? Yeah, equals 0.1427. You have 14% chance of exactly 3 women getting whatever selected. That's some pretty good odds.